So good morning, everyone, and welcome to the summer semester at UIC. In particular, we will be working together on the object of linear algebra. So this is linear algebra, applied linear algebra. What we would like to call Math 310. I will be your instructor for the semester. My name is Evangelos Kobotis. And my email is the office hours for this course are going to be Monday and Wednesday at 11:50 on this link. Now, I would like to, you see, I'm not even giving any limit to how long I'm going to stay with you. I'm going to stay with you as long as it takes so as to answer all of your questions. And but I will kindly ask you that if you plan not to come in the first 10 minutes, to email me so that I know that you will do so. Exactly because these office hours are on Zoom. Sometimes if I'm here for longer than 10 minutes and nobody shows up, I will most probably be leaving. Let me just say that in the recent past, this never happened. I always have had people coming to my office hours. So I think this will not be a problem. But I will just kindly ask you to let me know if your plan is to come later than 11:50 to my office hours, so that I will be there to assist you with anything that you require. Also, again, since this is not a physical office, in most cases, I will leave my answers open to everyone. You might actually hear a little bit of differential equations because I'm also teaching a summer course on differential equations. But if you ever come to my office hours and require to talk to me about an issue which is not related to the material of the course, but it has to do with it's some personal issue, then I will be putting everybody else in the waiting room and attend to whatever you have to tell me. And then when our meeting is over, I will be taking everybody out of the room. So this will happen a few times. Let me just begin by saying that the attendance for this course is mandatory. This course is synchronous. And the attendance is mandatory, which means that one of the prerequisites for you taking this course is that you can actually attend the course. So if your plan is to somehow take the course and try to bypass attendance or some other thing along these lines, then I will kindly ask you to consider dropping this course because it's not going to work for you. Also, when I say that the attendance is mandatory, that of course includes taking the exams at the proper dates, which, as you're going to see from the syllabus, are July 7th and August 4th. So we will have one midterm exam and then our final exam. There's a second requirement for you to be able to take this course, and this requirement is a camera. We're going to take our quizzes and our exams online, and it is important for you to be able to be on camera. And it is also important for you to configure your camera so that I can see this, which means yourselves and what you're writing. And we're going to do a test on Wednesday to make sure that everybody has a camera that can be configured this way. Again, this is one of the prerequisites for you being able to take this course. The reason for that, obviously, is that an important part of the coursework is related to the quizzes and the exams, and you have to be able to properly attend those so as to take the course. Does anybody have any questions, please?
So, as I understand right, Wednesday will be such testing for our cameras, not having actual test.
No, there will be no. What can I test you on Wednesday? I mean, we're going to do a little bit of material today, but there's nothing to test you on. Okay. Good question. I mean, I remember last year Friday was we had a day off because it was the Juneteenth holidays. This the same thing this year. To be honest with you, I have not checked the academic calendar. Oh, you're asking because I'm saying Monday and Wednesday are my office hours. No, it's just that I will have office hours twice a week. Let's just check the academic calendar now that you mentioned this. Let's take a quick look. And see if there's anything of note here. So it seems that we don't have class next Monday. Okay, so on Friday we will have a regular class. July 4th is not relevant to us. And yeah, okay, so we're going to miss just one class, which is next Monday. Okay, that's all. Okay, so everything else is scheduled as needed. Any more questions, please? Now, I would like to be a little more precise about the attendance because, it is possible that some of you will have some absences. And I would like to explain to what extent that those absences are okay. So you need to have at least 75% attendance. Okay, so as not to incur any letter grade drops. And if below 50%, then you will not be able to obtain a passing grade, or you will not be able to obtain a C for the course. Okay. This course has no discussions, so it's just a lecture. And there will be 3 pieces of coursework. So there will be one homework assignment assigned on every lecture. So Monday's assignment will be due on Wednesday midnight. Wednesday's assignment will be due on Friday midnight. And Friday's assignment will be due on Monday midnight. All the assignments will be on Gradescope. And you will see that I have already posted a first assignment for you to do for Wednesday, where all I want you to do is go over the class procedures reiterate the class procedures on the document and just upload it on Gradescope. This is strictly optional, and it's strictly optional. Okay, it's strictly optional.
Because it say 100 point in Gradescope. It says this would be 100 point in Gradescope.
Yeah, but I mean, there will be something assigned to it, but there will be nothing on your course record. Okay, so when I say it's optional, I truly mean it, but regardless, you're strongly advised to actually do it. Okay. So the quizzes are going to be taken on each class. I think our first quiz is going to be on Friday. I'm going to let you know about this. And there will be a total of 15 homework assignments and 15 quizzes. And I'm going to drop one of each, the lowest grade from each category. And at this point, I think it would be useful for each one of you to go to the syllabus. And let's see what we have. So what are the percentages for the different parts of the coursework? So the percentages are going to be, the quizzes are going to count for 15% of your score. The homework is going to count for 25% of your score. The midterm exam is going to count for also 25% of your score. And the final exam is going to count for 35% of your score. The cutoffs for A, B, C, and D are pretty much the same as they are for Calc 3. So 85 or better will earn you an A. 70 or better will earn you a B. 55 or better will earn you a C. Please note that I'm not going to do any rounding. And I know it's very, very unfortunate, but anybody who gets something like 84.99 actually receives a B. And again, my apologies in advance for any inconvenience that this might bring. Are there any questions, please? So as far as the rules of academic integrity are concerned, we will observe them in their entirety. So you're not allowed to submit identical homework or homework that can be seen to be the same. If you happen to work with somebody on the homework assignment, that's perfectly fine. But then when you're ready to actually write it out, please go your separate ways and submit different assignments. And I will kindly implore you, I kindly beg you to actually do this so that we don't have any unpleasant incidents during the semester. Same thing goes for exams and quizzes. I mean, in the past, I have always come across people who, regardless of how strongly I make these statements, they will still think that there is room for doing things that do not conform to any kind of academic integrity. And then when they get caught, they try to plead for overlooking the rules. And this is not going to happen. I'm telling you right now, it's being recorded. So please expunge completely from your system any kind of thought, will, desire to ever do something, share work, copy work, use resources that you're not supposed to for any of your coursework. It's not going to end well. So please do not do it. Does anybody have any questions, please?
Yeah, about the textbook. Do we will use a textbook?
No, not really. I have an open source textbook which I have posted on Blackboard, but my lectures are going to be self-contained, and there's really not going to be any need for the textbook, but it is there for as an extra resource for more examples and for some very interesting applications that are stated in the textbook. So it's not completely superfluous. I did not post it just for fun. I think it's a nice thing to have and to be able to consult every now and then. Any more questions, please?
Is this any material from the previous, I think, Mass 180 should to be reviewed?
No, this course is more or less self-contained. I mean, even though Math to 10 is a mild prerequisite for this course, you might argue that all you need in order to be able to take this course is high school algebra. I don't know. I mean, nothing, pretty much, just to know numbers. There is no discussion. Yes, there are no sessions attached to this course. Right. No, if my apologies regarding this. If it's mentioned anything about discussions, I believe that it could have been carried over from a different course. So no, there's no discussion. The attendance is taken strictly on the basis of lectures. Any more questions, please? Okay, then. So I believe that this is it. Then we can get started. Does anybody have any questions? I think we can get started. We're not going to have too much material today, but what we're going to begin with is going to be very, very important. So I would like us to take our time and discuss it very, very carefully. Okay, so let's what is linear algebra? Linear algebra is the study of vector spaces the maps between them and other relevant structures. Many of the concepts of linear algebra can appear in a concrete setup. By avoiding, in other words, the notion of vector spaces. So, in other words, these are concepts such as systems of linear equations, matrices, determinants. And it is true that the emphasis of our course will be exactly these objects. However, it will also be true that we're going to consider these notions in the theoretical framework of vector spaces, because vector spaces represent such a strong and ubiquitous tool that the study of vector spaces is going to really make our life easier when it comes down to understanding the rest of the concepts that we have mentioned. So linear systems of equations, matrices, and determinants. And this is why we will actually begin our course by explaining what a vector space is, and we will see how the rest of the concepts tie up with the concept of a vector space. So that's precisely why I would like to talk about vector spaces. So what is a vector space? It would be actually quite appropriate at this point to indicate through some examples vector spaces that you have already considered. First of all, the set of real numbers is a vector space, but that is not going to be that interesting in understanding what a vector space is. So from our experience, from what we have seen in the standard math courses, the set of two-dimensional vectors and three-dimensional vectors are examples of vector spaces. So set of two-dimensional vectors. What are the properties of two-dimensional vectors that allow us to say that they form a vector space? First of all, we had an addition of vectors. So given two vectors, we were able to find a third vector that we call the sum of the two vectors. And we were also able to scale a vector. So for example, if this was the vector u, then this would have been 2u, and this would have been -1/2 u. So we were able to scale vectors by any real number. And this is pretty much what we try to generalize when we talk about vector spaces. So let's write down the abstract description of what a vector space is. And we will see that the two-dimensional vectors and the three-dimensional vectors represent instances of vector spaces. So let's see what we have. So a real vector space, as we're going to see later, we have complex vector spaces or vector spaces over finite fields for that matters, but a real vector space V is a set consisting of elements referred to as vectors, and equipped with two operations. The first operation is an operation from V cross V to V, which is called addition. So two vectors u and v are taken to their sum, the way in the case of two-dimensional vectors, it is done in the geometric way that I showed a moment ago and you have seen in Calc 3. And we also have a possibility to scale vectors. So we will call this scalar multiplication. And here you have a real number lambda, your scalar. You have a vector v, and you attach to the two of them the scalar multiple of v. And again, please keep in mind the concrete example that I gave you about two-dimensional vectors in the previous page, where I told you that if you want to scale your vector by a factor of 2, you just keep the same direction that it points to, and you scale its magnitude by a factor of 2. If you want to scale it by -1/2, then you reverse the direction and you make the magnitude of the new vector 1/2 times the magnitude of the old vector. And these two operations are subject to 8 properties, 8 axioms. That satisfy. Let me see, there was a no, I'm sorry. This cross that you see here, I'm glad that you asked this. This cross that you see here means that I'm taking elements from 2 elements, one element from V and another element also from V. So that's what this means. And we're not going to go back to this too much. This is called the product of the two spaces. The important part for you is this part, meaning the fact that addition is represented by u plus v, and scalar multiplication is represented this way. Okay, this is simply when we write v cross v, that's simply the set of all pairs of vectors. And that's why we say that addition amounts to associating with each pair of vectors a new vector called a sum. Okay? So, so let's see what the properties are. So the first property is that when somebody gives you three vectors, how can you add them? You can take the sum of u plus v and then add w, or if you want to preserve the order in which you were given the vectors, you can take v plus w, so add first v plus w, and then add u. And the reason for that is because you can only add two vectors at a time, right? So there is a property that says, the very first property says that no matter how you choose to do it, so whether you do it as u plus v first and then w, or as v plus w first and then u, you're going to get the same thing. And as you very well know, this property has a name. It's called associativity. And you know what? Let me actually introduce you to some very useful mathematical notation that literally makes our life very easy. When you first see it, it looks very fancy, but let's explain it. Okay, this symbol, which is an upside down A, means for any. And this symbol means belonging to. And you will see that there is another very interesting symbol that I'm going to use, which is this reverse E, which means there exists. This is the common language of set theory. And unfortunately, it has been omitted from recent high school mathematics. But, you know, it will make our life very easy when we want to write things such as there exists or for any, belonging to. And this is something that we're going to do on a very regular basis here. Okay, does anybody have any questions on this notation? I'm going to, you know, explain it every time I use it so that this way it sticks with you. The second property says that there exists A in V, a vector in V, such that if you add this vector to any vector from either side, then you get the same vector. For any V in V. It turns out that whenever this, since this vector exists, it turns out that it is unique. Such a vector is unique, and it is denoted by, does anybody guess what I'm going to denote it by? Excellent, 0. Excellent, 0. So this will be the 0 vector. The 0 vector is by definition the vector that when you add it to any other vector, it doesn't change it. You get the same vector. And also, for any V in V, there exists W such that V plus W is equal to W plus V is equal to the zero vector, the vector that we just identified. And it turns out that W is also unique. Again, this requires a small proof. I will avoid proofs in this course. Okay, I promise you, I will avoid proofs. We said it's applied linear algebra. Okay, there are some summers where, for reasons that are not that bad, I did some proofs every now and then. Because V is the set of R vectors. V does not consist of real numbers. Okay, these are not numbers I'm talking about. And you will see later what are the most common examples of vectors that we're going to be using here. Okay, so there exists a W such that V plus W is W plus V is 0. It turns out that W is exactly, very good, minus V actually, not minus W, is unique and will be denoted by minus V. Okay, it will be called the opposite of a vector. We define U minus V to be U plus the opposite of V. That's why sometimes we think of addition. I'm sorry, we think of subtraction, and this is how you define subtraction. We think of subtraction as an auxiliary operation, or as an operation that is based on addition and the existence of opposites. Finally, U plus V is V plus U. So the order in which you do the operations is not relevant. So it's equal to V plus U for any U comma V in V. This is called commutativity. And at this point, it should be nice to note that any structure satisfying conditions 1, 2, and 3 is called a group. Groups form the basis of abstract algebra. If commutativity is also satisfied, then we talk about an abelian group. The word abelian comes from the mathematician Abel, an incredibly ingenious individual who had a kind of very short passing from this world. And then we continue with the fifth axiom, according to which if you have the sum of two numbers and you want to scale a vector by a sum of two numbers, then you could scale the vector separately by each number and then add the corresponding scaled version. So for any real numbers, lambda in U and any U in V. So this is clearly what we call distributivity. And we have a similar distributivity property for addition of vectors. So if you want to scale the sum of two vectors by a number, then you can scale first the first vector, then the second vector, and then add them up. So for any lambda in R and any U comma V in V. If you scale a vector by the number 1, you will always get the same vector. And if you, last but not least, if you scale a vector by the product of two numbers, you could actually scale it first by one number and then by the other. And that's it. These are the 8 properties that establish that a given set with 2 operations given in advance is a vector space. And I'm going to give you the one example that will be the most important example. So there is a question about, I believe, this symbol right here, right? So this is, let me write them in a slightly larger version. So again, this letter is denoted by lambda. It's a standard letter for scalar numbers. You've seen it in Calc 3. If you want the simplest way to write this, then do this, okay? My kindergarten teacher, God rest her soul, would have not been too happy with this, but you know, it can do it. The other symbol is this symbol, which is read mu. And again, to understand how you do mu, it's like pretty much a U without the extra line, and then with a little line like this. So that's mu. And these are the some of the numbers that we some of the letters that we use in a standard way in linear algebra. Obviously, you have seen lambda with Lagrange multipliers. And if we ever did that, which is not something that we actually did, you can have the method of Lagrange multipliers in Calc 3 for more than one constraint. When you have more than one constraint, usually if you have two constraints, the second letter that you use is mu, for example. That's why lambda and mu go together, and they're next to each other in the Greek alphabet. Any more questions, please? Okay. So look, one can give pretty diverse examples of vector spaces. They all usually boil down to the same thing. But for us, there is absolutely one example that we need to know. One example and one example only. And this example is the example of Rn. What is Rn? Rn consists of all n tuples of numbers Sometimes you will also call this, so let's see, we have different ways to describe this mathematical object. So we can call it an n tuple of numbers. We can call it a column matrix. Or more specifically, an n by 1 matrix. You can call it any of those things. And we will have an alternative for this. So either we will denote it this way, or we will denote it with A1, A2, AN, and the T. This T stands for transpose, transpose. And the reason we will denote it like this is because it's easier to write it in rows in one line than writing it in columns. And I'm going to do a slightly transgression here, and I'm also going to put commas. The commas are going to clearly separate the numbers. The truth is that I shouldn't be putting commas, but they will make our life easier. And that's the reason I'm going to denote them like this. And of course, I have to tell you how we add and how we scale such vectors. So the first bullet point is n-tuple, n-tuple. So the word tuple is like we say a triple, a quadruple, a pair, a triple, a quadruple, an n-tuple. So a collection of n objects. So that's what an n-tuple is. So an n-tuple is a collection of n objects. Okay. The good news is that there's not too much more terminology other than the one that I'm giving you today. These are the great news. So some people might see this and might say, oh, that's too much new math in one day. But the good news for you is that that's it. We're going to pretty much work with these objects for the rest of the semester. Okay, so I don't, and if some of you feel a little concerned about these objects today, next week you will be just fine. They will come to you as natural as numbers, pretty much. Okay. So I know the worries that one can have while being exposed to this material for the first time, but I can assure you that everything will be quite smooth. However, now I have to show you how to add and subtract, how to add and scale these things. And I almost, I can almost tell you that this can be done in a very intuitive way. So let's see if you can guess it yourselves. So let's say that I have to add two such vectors in Rn. So A1, A2, up to AN. You know what? Let's do something funny. Why don't we do it in R4? R4 is as generic as Rn. So let's say that I want to add two vectors. Can you guess from your experience with vectors in Calc 3 what the sum of these two vectors is going to be, so that we can write colon equal. Colon equal means to be defined as. So let's define it as what? Can you guess?
Excuse me, why the small t in the B numbers inside?
My bad. I was being distracted by a telephone that was ringing in the background. Thank you so much. Thank you. It should be outside. Okay, so can anybody guess what the sum of these two vectors is going to be? Yes, exactly. That's precisely right. So it's going to be A1 plus A2. I'm sorry, A1 plus B1. A2 plus B2. A3 plus B3. A4 plus B4. And can anybody guess what lambda times the vector A1, A2, A3, A4 is going to be? Again, let's put a colon equal, which means to be defined this way. Can anybody guess what it's going to be? Again, T stands for transposition. So instead of writing it as a column, we make our life simpler and write it as a row, but by putting the T, we remind ourselves that it is really a column. Okay. So can anybody guess what the scalar multiple is going to be? Exactly. That's what it's going to be. Lambda multiplying each one of them. And now that we gave this definition, why don't we do some concrete examples so that we can all get a feeling about how this is done? Okay, so why don't we do this? So let's say that you are in R3. Let's write them as columns now. So 1, 2, -1, plus 3, 7, 10. And if you do this, could you also please do twice 1, 2, -5? And could you also please do -4 times 3 to -1? We can also solve equations if we like. So if somebody were to tell you that you have an unknown vector u, which when you add 3 times the vector 1, 3, -1, it will be 2, 7, -3. What I'm going to post on Blackboard is the recording of the lecture, but I strongly advise you to try to follow along and keep your own notes. Okay. So let's try to find the answer to all of these things. Okay, why don't we look at them together now? So the first one is going to be 4, 9, and 9. The second one is going to be 2, 4, and -10. The third one is going to be -12, -8, and 4. And now for the last one, I'm just going to treat them as real numbers. So I'm going to say u is equal, u And you know what? I'm sorry, too much calc 3. I will not be putting arrows here. So u plus 3, 9, negative 3 is equal to 2, 7, negative 3. And u is equal to 2, 7, negative 3 minus 3, 9, negative 3. And eventually u is equal to 2 minus 3 is negative 1, 7 minus 9 is negative 2, and negative 3 plus 3 is 0. Do we all agree? Okay, great. I mean, you will see, like I said, at first glance, it sounds a little strange, but here's what I want you to understand. And let me recap. Our object is vector spaces, right? But among vector spaces, we're not going to just start studying indiscriminately any vector space there is out there. We're going to specifically limit ourselves to this particular vector space, Rn. And at this point, some of you might be a little disappointed. Some of you might be saying to yourselves that, but you're telling us that there are all these interesting vector spaces out there, and now you want us to stick with you and just limit ourselves to Rn. And yes, I'm saying exactly that. Because as you're going to see, Rn is not just an example of vector space. It's the example of vector space. By understanding Rn, I'm not actually promising that you understand all vector spaces, but you understand the finite dimensional ones, which are the ones that show up in most elementary applications. Yes, there are also infinite dimensional vector spaces. I promise you that I will find some time to talk about them a little during our course, but our course is really about finite dimensional vector spaces, and dimension is something that we're going to explain next time. So in some sense, you will see that we will not have a particular need to go back to the axioms. Yes, it would be great for any one of you to actually memorize these axioms and remember them, but we're not going to use them. Why? Because we're working with a specific example of a vector space, and that specific example is Rn. So in some sense, our treatment is not any more theoretical than the usual treatment of this course in the semesters. However, at the same time, we grab this opportunity to know what a vector space is, to know that what we're looking at is an example of a vector space. And there's going to be one notion that will be very, very useful that we're going to see next time. And it is very useful to see it in the context of vector spaces. Questions, please.
Why did you took the arrow from the U?
Excellent question. So first of all, you will see that in my notes, I'm going to use bold U for vectors. In many, many books, you will see that the bold letter is used. You will also see the arrow. You will also see sometimes the wedge, or you will also see a tilde underneath. These are all valid notations for vectors. But basically, I will be sticking to this notation. It's just the choice that I'm making. And I will not make any attempt to make my letters bold. Okay, so in the context of R3 or R2, meaning the vector spaces that you encountered in Calc 3, this helped you really differentiate between letters, between scalars and vectors. But you will see here, the context will be usually very, very concrete, and we will not have any big problem. Plus, in abstract linear algebra, it's almost never the case that we use arrows. We just use letters, sometimes bold, sometimes not even bold. Okay, so this is just common practice. Questions, please. Any more questions? Now, I would like to also give you an idea of how we can view systems in the context of Rn. So let's say that somebody gives you a usual 2x2 system. So they tell you, 3x plus 2y is equal, I'm sorry, apparently there is one more question. Let me see if I can address it. Yes, you can show your work either in columns or in rows. You will see me using the row with T. Don't forget the T if you put a row. I mean, we're not going to take it to be a mistake, but please don't forget it. And the reason I don't want you to forget it is because, as you're going to see later, there are also going to be row vectors. So vectors that are directly rows, not columns. Somebody might be asking, is this ridiculous or what? Why do we have to write things in columns? So why don't we write them in rows? And I don't have a good answer for you today, but I promise you that there will be a good answer later in the semester. So, so let's say that you have something like 3x plus 2y is equal to 7, and 4x plus 9y is equal to 1. And you're asked to solve this system. I mean, many of you can possibly solve this system. Some of you may have seen even Kramer's rule or anything of that type. But what I want you to understand is that a system of this type can be written immediately in terms of vectors. How? You could say x times 3, 4, the vector 3, 4, plus y times 2, 9 is equal to 7, 1. Or if you like, I could rewrite this as x times the vector 3, 4 written this way, plus y times the vector 2, 9 written this way is equal to the vector 7, 1. So a system can be considered immediately as an equation inside the vector space R2. Okay, so this is the kind of identifications that we're going to make throughout the course. And you will see that in some sense, working in Rn is the same thing as considering things simultaneously in n copies of R. In n copies of R. So when we work with R4, is like having 4 sets of real numbers and doing things simultaneously on those 4 sets of real numbers, pretty much. So this is something that you're going to see pretty soon. Okay.
Oh, excuse me. What do you mean by the small t?
Again, the
What
small
do you
t.
mean? What do you mean by the t you put everywhere? So,
as I said before, if I write it this way, I really want to write it this way. I really want to write this, but I don't want to keep writing columns. So what do? I write a row, and I put a t, which means transpose 3, 4. Transposing 3, 4 means by definition to put it as a column. You will see later that the transposition of matrices in linear algebra amounts to making columns into rows and rows into columns. So for us, 3, 4 with a T is the same thing as if we had written a column. It's just much simpler to write it as a row. But when we write it as a row, we want to remind ourselves that it really is a column, and that's why we put a T. Okay, so it's a notational. It's for our notational convenience, if you will.
Thank you.
Any more questions, please? Okay, I think I'll leave it at that today. I would really like you to review what we have done very, very carefully. Why? It's not just something that we will do now and then move on to something different. It is what we're going to be engaged with throughout the semester. So throughout the semester, we're going to talk about vector spaces. As you're going to see, we're going to talk about vector subspaces, something that we're going to discuss on Wednesday. And we're going to be talking specifically about Rn. And this is why I would like you to make sure that you become comfortable with these notions. They're going to become our bread and butter for the rest of the semester. Are there any more questions, please? So don't forget to do this homework for Wednesday. I'm going to post this lecture in the next half hour or so when it becomes available to me by Zoom. And I will see you again on Wednesday. Okay. Have yourselves a very nice day.
Thank you.
You're very welcome.